Hello everyone, and welcome to today's chem lesson. Today, we are going to continue our discussion on oxidation and reduction. Last time we looked at half reactions and what it looked like when one thing was oxidized, or what it looked like when one thing was reduced. But you cannot have oxidation without reduction, and you cannot have reduction without oxidation. One needs the other. And so we often don't talk about the individual halves. Much more often we talk about the whole. What happens when you have reduction and oxidation together? A redox reaction. A redox reaction occurs when one part of the reactants is oxidized and another part of the reactants is reduced. So it takes the reduction and the oxidation, those two half reactions, and it smushes them back together to make the whole reaction, the redox reaction. When we're looking for a redox reaction, we are looking for substances to change their oxidation states. Now, what does that look like? We know an element by itself, a pure element, has an oxidation state of 0. So that means both of these things have oxidation states of 0. And we know that the oxidation state of something in a compound is not 0. They add to 0. The two of them together are going to sum up to 0. But within the compound, one will be positive and one will be negative. So in this case, the sodium went from 0 to a positive 1, right? We check our periodic table and we look for the oxidation state in the upper right hand corner. The Cl went from 0 to a negative 1. So did those oxidation states change? Absolutely they did. That makes this a redox reaction. The sodium went from 0 to +1. The sodium was oxidized. The chlorine went from 0 to -1. The chlorine was reduced. Another way of saying this, another way of thinking about this, is that sodium gives electrons to chlorine. Right? If sodium is oxidized, that means sodium is losing electrons. If chlorine is reduced, that means chlorine is gaining electrons. And so the thing that's happening in this reaction is sodium is giving electrons to chlorine. Those electrons are being given from the from the thing that is being oxidized to the thing that is being reduced. Let's try a practice. Is this reaction a redox reaction? Yes or no? This reaction is a redox reaction. Again, when we're looking for a change in oxidation state. Pure elements have oxidation states of 0. Within a compound, they add to 0, but the H's are positive 1s and the O's are negative 2. So the oxidation state change here is from 1 to 0 for the H's, from negative 2 to 0 for the O's. So in this case, which thing is oxidized, which thing is reduced? In this case, the oxygen, the two O negative 2s, become O2, 0, and give up 4 electrons. The O is oxidized in this case. while the H's gain 4 electrons and become 2H2. Right, just taking apart this reaction to give us the two halves of that reaction. Let's try another one. Is this a redox reaction? Is there a change in oxidation state between the left and the right? In this case, the answer is no. This is not a redox reaction. The Na is a +1, O minus 2, H +1, +1 minus 1, +1 minus 2, +1 minus 1. None of these elements, none of these ions have changed their oxidation state. The Na is a +1 on the left, it's a +1 on the right. The O is a -2 on the left, it's a -2 on the right. The H is a +1 on the left, the H's are a +1 on the right. Cl is a -1 on the left and a -1 on the right. There is no change here, so this is not a redox reaction. The ions got rearranged, right? It was a double replacement that just happened here, but it is not redox. There is no reduction. There is no oxidation. How about another? What about this one? Is this a redox reaction? This is a redox reaction. The magnesium as a pure element is a 0. The H2 as a pure element is a 0. The magnesium in a compound is definitely not 0. Again, we know that these are going to add up to 0, but in this case, it's a +2 and a -1 for the magnesium and the chlorine. The HCl is a +1 and a -1. You don't need to know what the oxidation states are in this case, right? No one's asking you to find the oxidation states. But you know a pure element is a 0, and you know that an element in a compound is not 0. That means that one of these things changed oxidation states. That means this is a redox reaction. To take a closer look, in this case, the magnesium is oxidized, going from 0 to a +2, losing 2 electrons. And in this case, the 2 H pluses are reduced to become H2. Oxidized, reduced. All right, that is our redox. Let's look at a Regents practice problem, worded a little bit differently. What happens to the aluminum? Keep in mind they're saying specifically Al, so this Al, what happens to this Al in this reaction? In this reaction, the aluminum loses electrons. Let's look at it from left to right. It starts off as Al0 and becomes Al +3. The oxidation state went up. It went from 0 to a positive number. That means it lost electrons. That means it was oxidized. If we wanted to write that half reaction, we would say aluminum 0 becomes aluminum +3. loses 3 electrons. If we wanted to be super accurate, we would include the coefficient that they gave us in the question. And this 3 would actually become a 6. Because 2 aluminums become 2 aluminum plus 3s, each one losing 3 electrons. Now, we're going to look at this format. We're going to look at this equation format a little bit more closely. Why do I need these coefficients? Couldn't I just go 1, 1, 1, 1 and have a totally perfectly balanced equation? Why would the Regents give you 2, 3, 2, 3? What's the point of the 2, 3 and the 2, 3? In this case, it's because we need the charge to be balanced as well. Like I said, this pair of aluminums is going to collectively lose 6 electrons. There cannot be an oxidation without a reduction. And not only do they have to both happen, the amount of electrons exchanged needs to be equal. How can the aluminum lose 6 electrons if there isn't something else ready to take 6 electrons? The copper plus 2 can take 2 electrons to become copper 0, right? That's what this is telling us here. But 2 is not equal to 6. I need 3 copper 2s to each take 2 electrons in order for this to be balanced. 6 electrons lost, 6 electrons gained. And just like in math, when you add 2 equations together, the stuff on the left side goes on the left side together. Stuff on the right side goes on the right side together. Alright, here's our left, here's our right. And something that appears equally on both sides gets canceled out, which is why we never see the electrons in a fully balanced redox reaction. Let's take some notes on that. Right? We already know that in an equation you conserve matter, right? We talked about balancing equations. We know that if I have Al on this side, 1 aluminum, I need 1 aluminum on the other side of the arrow. But we never really looked at conserving charge before, because all of the equations that we've looked at so far or something like this. Where the oxidation state of each thing was 0. So overall, the charge balanced out. It had to. But when we start getting into reactions that have naked charges, right? What do you mean by that, right? When I get a reaction that has a charge that's just kind of hanging out here, I need to make sure that the charge is balanced as well. Right? The electrons that are lost by the thing that gets oxidized must be equal to the electrons gained by the thing that gets reduced. And just like I did about a minute ago, where I took apart and wrote the half reaction for the oxidation and the half reaction for the reduction, and we saw 6 electrons gained and 6 electrons lost, that same concept is going to apply here. It's the exact same thing. the charge on the left needs to equal the charge on the right. We already know how to balance it with matter. We already know that the amount of H's on the left need to be equal to the H's on the right. The Cl's on the left need to equal the Cl's on the right. But the charge on the left needs to equal the charge on the right as well. Let's do a little bit of practice with this. Is this equation balanced? The answer here is yes, it is balanced. Let's check. All right, I've got 3 iron on the left. I've got 3 iron on the right. 1 aluminum on the left. 1 aluminum on the right. So mass is balanced. But what about charge? Let's take another approach and look at charge. I have 3 positive 3s. That's a total of a positive 9. I have 1 0. So my total charge on the left is positive 9. How does that compare to the right side? 3 positive 2s. That means plus 6. 1 positive 3. That gives me a total on the right of positive 9. So is my charge balanced as well? Yes, it is. Both mass and charge are balanced. Again, this only matters if I've got an equation that has these naked charges. I need there to be these charges hanging out in order for me to care about this. If you look back when we did our balancing equations, if you look back at our acids and bases, there really was never any time where we had naked charge like this. Just charge hanging out. Now that we have charge hanging out, we need to make sure that it's balanced, that the charge on the left is equal to the charge on the right. Let's try a Regents version of this. Balance this equation, and then what is the sum of the coefficients? If you're not done yet, pause the video. We're going to go over this one now. Here, the correct answer is 1. Choice 1, sorry. 10. How did we get that? We balanced the equation. Not only do we need the amount of mg's to be equal on both sides and the amount of CR's to be equal on both sides, we need the total charge to be equal on both sides. Here we got 0 and positive 6. Here we get positive 6 and 0. So our left and our right are equal. Now, did you have some trouble with that? Let's take a look at how you approach that. You know you have positive 3 as your only charge on the left. So you could get positive 3, positive 6, positive 9, positive 12, right? It has to be a multiple of 3 because you can only put whole numbers in this spot. On the right, you only have positive 2's that you can use because the CR is a 0. So you know this must be a multiple of 2. 2, 4, 6, 8, 10, 12. And you're looking for the smallest common factor. Alright, you know that this must be a multiple of 3, this must be a multiple of 2. The first place that they overlap is 6. You're trying to make sure that these are equal. And just like when we balanced equations normally, this is a little bit of trial and error. All right, you're going to plug in a 1, does that work? You're going to plug in a 2, does that work? You're going to plug in a 3, does that work? You're going to plug in a 4, does that work? Work your way up, trying to make them balance out, trying to make those charges on the left equal to the charges on the right. Let's wind it down with one more practice problem. What is the total number of moles of electrons needed to completely reduce 6 moles of Ni plus 2 ions? How many moles of electrons will you need? In this case, we're looking at 12 moles of electrons. Why 12 moles? If we want to completely reduce or completely completely reduce means bring it back to 0. So if we have Ni plus 2 and we want to go to Ni 0, we need 2 electrons. But we don't just have 1 mole of nickel, we've got 6 moles of nickel. So we're going to need to do that 6 times, meaning we're going to need 12 moles of electrons. Next time, we're going to get into how we use this. How can we take advantage of the movement of electrons from one thing to another? The thing that gets oxidized gives the electrons to the thing that gets reduced. How can we take advantage of that? How can we take electrons moving from place to place and make something positive out of that, make something good for us? How do batteries work? How does electricity work? It works through this concept, moving electrons from place to place. But that is a topic for next time. For now, have a fantastic day.